So now we're going to start with line 13. There's quite a bit of data with this, so it might end up having more than one video. Okay. Just so you know, for number 10 and 11, the videos, I gave the title of the actual video, but it got changed because I had 3 videos instead of 1 from number 10 because of all the data that came up from it. So it looks like 13 is going to do the same thing. So just before 1, there might be 3 parts to this video. So line 13 is SETI Mersenne number, binary rep units, quadratic functions, Evariste Galois theory, linear algebra, plane Euclidean geometry, and 8191 Mersenne asteroid, and the split-radix algorithm. That's what this video is going to be all about. This one's for part 63, and so what we're going to do is I'm going to bounce around here. I've got my thoughts there at the end, and I'm not going to do that till I get through some of this material. I'm not sure if I'm going to go through all of it or if I'm just going to do a quick briefing because it is very dry. And what I might do is just put it up on the blog, the Victoria Stafford Psychic Investigation on WordPress, just so you can look at the information and click on the links to see all the stuff I found from this line on the WOW. Line 13 is just basically, it's not a math equation, it's just numbers 3, 7, and 1, right? As you notice that Jerry Eyman actually circled the number 7. I don't know why he did that. And he circled the number 6 as well. So he's got number 6, number 7, and then he's got the actual alien signal that came through the 60QUJ5. Okay, so what I did was I looked at the spacing between the numbers. So I've got number 3 with 1 space, then a 7, then 2 spaces, and a 1. So I typed it up on my typewriter, my computer, and I googled those numbers to see what comes up, and all of this information came up, and it all has to do with spaceships and math. So anything to do with ancient math I always put on here, because you never know, this might be the stuff that you need to use to get your faster spaceship. This technology is for scientists and physicists, people in the physics and science world to look at. You can look at it, you can come up with some new theories, and I'm hoping you'll come up with some new inventions and stuff out of this as well. So these are the tags for this video: the Vedic mathematics sutras, Mersenne number of prime, decimation and frequency split-radix algorithm for computing new Mersenne numbers transform. So basically what happens is I got a topic on this video that I can't fit into the title, I put it into the tags. So I'm starting to do that because I'm finding on YouTube it's not letting me upload my videos because my lines are too long, because I'm long-winded, as we all know. Okay, so I'm just kind of cutting them down so they're a little shorter. Yeah, that's right. Now the reason this title is so big is because I think there's going to be more than one video here, and I will probably divide this up to line 13A, and then I'll take whatever's in that video, and then line 13B, and I'll take the rest and I'll copy and paste it, and you'll know what it is after that, okay? So this title could change. So the Mersenne number is from Wolfram Math World. Thank you very much for having this on your blog. And his blog is mathworld.wolfram, WOLFRAM.com if you want to take a look there. It says it's an integer. The Mersenne number consists of all 1s in base 2, and they are therefore binary rep units. So the reason I grabbed this is number 1 comes up, which is quite prevalent in the WOW signal, as you can see. Loads of 1s, right? And then it also says binary rep units. Well, binary code is what this is called. So I grabbed that. And then the next one is, he shows the form of it. It's an integer. It consists of 1s and 2s rep units, and it shows how a binary unit works. Numbers of digits, log numbers, and then it shows all these numbers here. So this is basically the data that I found on the website. Those are references, and that's from mathworld.wolfram.com. Mersenne number, if you want to Google that, you can look up that information that he's got there. Okay, so as you know, on my videos, left side's data, right side is the stuff I pull out from the data to see what we can use, okay? So in mathematics, a Mersenne number named after Marin Mersenne, a French monk who began the study of these numbers in the early 17th century. So here we go with the 17th century coming up again. is a positive integer that is 1 less than a power of 2. And that's what the equation looks like. Some definitions of Mersenne numbers require that the exponent p be prime, since the associated number must be the composite if prime is composite. And that's from Wikipedia, Mersenne prime. Okay. So another word that comes up is quadratic function. That's what it looks like. And it's a real variable of coordinates, points where the graph intersects. And I saw a lot of these types of graphs when they were looking at the planets and stuff. So I pulled this out. It shows the different lights and stuff. That's kind of like spectrum. And it's quadratic functions. And it's showing how they vary. Different angles and stuff that they use for A, B, and C. And that's on Wikipedia. So I looked up the word quadratic equation because I didn't know what it meant. And let's go down here. So in mathematics, a quadratic equation is a univariate polynomial equation. Now you're going to see the word polynomial equation that comes up a lot. Of a second degree. A general quadratic equation can be written in the form of ax to the power of 2 plus bx plus c equals 0, where x represents a variable or an unknown, and a, b, and c are constants with I don't know if it's not equal to 0. If a is equal to 0, the equation is a linear equation. So we have the linear equation. That came up in our earlier videos, either in 10 or 11. The constants a, b, and c are called respectively the quadratic coefficient, and blah, blah, blah. Okay, so quadratic equations can be solved by factoring, completing the square, graphing, Newton's method, and using the quadratic formula given below. So that's what it's used for. And that's under WIKI quadratic equation. It's also used for solving complicated mathematical problems. It's done by using complicated formula like a quadratic equation. So they use these equations to solve big problems, like math problems. The Babylonians, one of the earliest and progressive civilizations, was the Babylonian civilization. They were known to have used quadratic equations in a limited sense. That's on www.whoinventedit.net. That's a cool site to go to. Next is called the resolvent Galois theory. I don't know if I'm saying his name right, so forgive me if I've got it wrong. So this is Galois. Look how young he is. He's just a young guy. And he was Evariste Galois from 1811 till 1832. Oh, he didn't live very long. Not even 21 years, poor guy. I wonder what he died of. In mathematics, more specifically in abstract algebra, Galois' theory, named after Evariste Galois, provides a connection between field theory and group theory. Using Galois theory, certain problems in field theory can be reduced to group theory, which is in some sense simpler and better understood. So we look at what is it for. It's the resolvent Galois theory for a permutation group G, which is a polynomial, there's that word again, whose coefficients depend polynomially of the coefficients of a given okay, whatever, I'm not going to read all that. But it's about something about to do with groups. And then the resolvents, which is a newer form of this type of math, is introduced by Joseph Louis Lagrange and systematically used by Evariste Galois. Nowadays, there are yet a fundamental tool to compute Galois groups. So that's what it looks like. x2 to power 2 is where triangle is the discriminant, which is one for the alternating group. There's a cubic resolvent of a quadratic equation, which is resolvent of a Darwin group of 8 elements. Here's the next thing that comes up is two intersecting planes in three-dimensional space. It's called plane geometry. This is something they would use in airplanes and spaceships by the looks of it. Two intersecting planes in three-dimensional space. In mathematics, a plane is a flat two-dimensional surface. A plane is a two-dimensional analog of a point, a line, and a space. Planes can arise as subpasses or some higher dimensional space, as with walls of a room, and they may enjoy an independent existence in their own right, as in the setting of Euclid geometry. Euclidean geometry comes up very many times. Okay, when working in two-dimensional Euclidean space, the definite article is used, the plane, to refer to the whole space. Many fundamental tasks in mathematics, geometry, trigonometry, and graph theory and graphing are performed in two-dimensional space, or in other words, in the plane. Okay, I might be wrong about it being for airplanes. I just guessed that, okay? So if I'm wrong, I'm wrong. You know, I don't know anything about this stuff, but this is what comes up with line 13 from that one little equation. WIKI, just look up plane in mathematics. Okay, so this is an implication of Einstein's theory of general relativity, is that Euclidean space is a good approximation to the properties of physical space, only where the gravitational field is not too strong. So, gravitational field, that's what you get on planets and stars, so I grabbed that. And then Euclidean geometry. As suggested by the etymology of the word, one of the earliest reasons for interest in geometry was surveying. And certain practical results from Euclidean geometry, such as the right angle properties of the 3, 4, or 5 triangle, were used long before they were proved formally. The fundamental types of measurements in Euclidean geometry are distances and angles, and both of these quantities can be measured directly by a surveyor. Historically, distances were often measured by chains such as Gunther's chain, and angles using graduated circles, and later the theodolite. Never mind. An application of Euclidean solid geometry is the determination of packing arrangements, such as the problem of finding the most efficient packing of spheres in n dimensions. This problem has applications in error detection and correction. Geometric optics uses Euclidean geometry to analyze the focusing of light by lenses and mirrors. So the reason I pulled that is there's lenses and mirrors on our satellites, the ones they're using, like the James Webb Telescope and also the SETI satellite. They look at this information when they're looking at the different planets and stars to see if they're habitable. So here's a function 7 times 8, 56, and then it shows, remember the ancient math like we talked about at the very beginning? This shows how they used to do it and how they come up with their multiplication, and that's how they used to multiply. 7 times 8 equals 56, then it shows how they do it. 3 is the difference from base, and 2 is the difference from base. Okay. So, and then there's also the Vedic mathematics sutras. And this is the central end point of the seahorse tail, is also a Measure-Witch point. Okay, so I'm going to define Vedic mathematics as a system of mathematics consisting of a list of 16 basic sutras or aphorisms. They were presented by a Hindu scholar and mathematician Bhai Krishnacharya Mahara during the early part of the 20th century. A Measure-Witch point is a parameter in the Mandelbrot set, the parameter space of quadratic polynomials, there's that word again, for which the critical point is strictly pre-periodic. It becomes periodic after finitely many iterations, but not periodic itself. Next is spherical geometry. This is a great circle on a sphere. The basic elements of Euclidean plane geometry are points and lines. And next, this is the R3 vector. Linear space and lines and planes passing through the origin are vector subspaces. In R3, subspaces are a common object of study in linear algebra. So that's in linear algebra example. And here's more about linear algebra. It's a branch of mathematics that studies vector spaces, also called linear spaces, along with linear functions that input one vector and output another. I'm not going to read all of that information, so I'm just going to do the bold spots. Linear algebra is central to modern mathematics and its applications. An elementary application of linear algebra is to find the solution of a system of linear equations in several unknowns. More advanced applications are ubiquitous in areas as diverse as abstract algebra and functional analysis. Linear algebra has a concrete representation in analytic geometry and is generalized in operator theory and in module theory. It has extensive applications in engineering physics, natural sciences, computer science, and the social sciences, particularly in economics. Nonlinear mathematical models can often be approximated by linear ones. Okay, so we're running out of time on this video, and like I said, we're going to have 2 videos for this section for line 13. This one here is in mathematics, the theory of linear systems is a branch of linear algebra subject which is fundamental to modern mathematics. Computational algorithms for finding the solutions are an important part of numerical linear algebra, and such methods play a prominent role in engineering, physics, chemistry, computer science, and economics. A system of nonlinear equations can often be approximated by a linear system, a helpful technique when making a mathematical model or computer simulation of a relatively complex system. So they would use this type of information probably to do their computer data for the Kepler system as well. So there's a box showing a linear system in 3 variables determines a collection of planes. There's the planes. The intersection point is the solution. Okay. And as you can see, I've got. Okay, so the next video is basically going to be a little bit more about an asteroid and my thoughts. So I don't have too much here, actually. I wonder if I can get away with it. So the next video is just going to be a summing up of this one, okay?